Hi guys, welcome to week 3. The topics that we're going to learn in week 3 is reaction kinetics. Now what is that reaction kinetics? It's actually related to the rate of reactions. We actually learned this in Sem 1 as well, about the rate of reactions, about the catalyst, how catalyst actually affects the activation energy, the types of catalysts that we need to know, which is homogeneous catalyst and heterogeneous catalyst. So it's all about the rate of reactions. But in this semester's for Sem 3, we're going to learn reaction kinetics in terms of orders of reactions. Now, these are the learning outcomes. So number 1, must able to determine the rate of reactions. What are the methods that we can use to determine the rate of reactions? All right. Second one is to able to determine the order of reaction. Now, that's the main thing in this topic, order of reactions, and to calculate rate constant. Learning outcome number 3, able to draw and identify graph based on order of reactions, and able to determine rate determining step, RDS. So these are the main learning outcomes that we need to achieve at the end of this week 3. Now first we look at how to measure rate of reactions. Now what are the methods that we usually use to measure the rate of reaction? Let's say for example I have a reactions between zinc plus HCl. We are going to get zinc chloride plus hydrogen gas. And the second thing, of course, we need to balance it, 2HCl. Okay, just looking at these reactions, we have zinc, which is a solid, HCl aqueous, zinc chloride aqueous because it's a soluble salt, and this is a gas. So what do you think? How do we measure the rate of reactions? Now, first, you need to be clear about what is rate of reactions. Rate of reaction is actually the change in quantity over the total time taken for the reactions. Now the change in quantity here, it can be referring to concentration of certain reactants, it can be referring to volume of gas, okay, and it can be referred to as the change in mass. Alright, so we have concentrations, we have volume of gas, we have mass. Okay, any changes to either one of this, measuring over time, we get the rate of reactions, how fast the reaction proceeds in a given time or in a given durations. All right, so in this case, if you look at the equations again, we have zinc solid at the beginning, and we have HCl aqueous. Now HCl aqueous is colorless, so we can't see anything. So we don't expect any visible change from there. But then for zinc, it's a solid. All right, we can actually measure the mass change. For zinc, initially, let's say I put in 2 grams of zinc. Okay, so when the reaction's ongoing, what happened to the 2 grams is supposed to decrease over time. So from 2 grams, it may drop to 1.5 grams, it may drop to 1 grams, and then at the end, it dropped to 0.5 and 0. So the decrease in mass of zinc can be used to measure the rate of reaction. That's one way. Another way is we look at the products. So on the product side, we have zinc chloride, which is soluble and colorless. So and again, we don't expect any visible change here, but then there's another product, we call that as hydrogen gas. So it's a gas. So we can measure the amount of gas collected during the reaction. So we can use the inverted measuring cylinder. Okay, the inverted measuring cylinder, we have these things like that, and then we have a delivering tubes like that. So we collect the gas here. Okay, this is water with the basins, and this is the reaction flask. So the reactions happening here, the gas will be transferred all the way to this and displace the water, and then we collect the gas here. Of course, this is a measuring cylinder. We have a skill to measure the volume of gas collected. All right, so we can measure the gas. So this is another way. But what about in terms of concentrations? Now, in terms of concentration, we can measure it using titrations. So let's say we have HCl at the beginning as a reactant. So let's say initially I'm using 2 mole per dm cube, and the volume used is 25 cm cubic. See that? So from here we can actually get the mole, right? So mv over 1000, so 2 times 25 over 1000, you get the mole of HCl. So we let the reaction proceed. Let's say zinc started to react with the HCl. Okay, we let them react for, let's say, 2 minutes. Okay, we fix the time interval. We let them react for 2 minutes, and then after that, we quench the reactions. Now, what is the meaning of quenching? We need some space here. Now, quenching of reactions. Look at that. So initially, I have a conical flask. I allow zinc and HCl to react, and we know the initial mole, right? From just now, we calculate 2 mole per dm cube times 25 over 1000. We get the initial mole of HCl. So we allow them to react for 2 minutes. After 2 minutes, what happened is we put into an ice bath. Okay, we put it into an ice bath, and what happened when the temperature dropped to 0 degrees C or low temperature, what happened is the rate of reaction would drop to its minimum. All right, so quenching means we pause the reactions. We stop the reactions temporarily, all right, and then so that we can now pipette out the solution into another conical flask. Let's say total volume here 25, right? We add in 25 centimeter cubic of HCl, and zinc is a solid, so it doesn't affect the volume. But then when we quench the solution, the reactions now is temporarily stopped after 2 minutes, and then we pipette out certain volume, let's say 5 centimeter cubic or 10 centimeter cubic. We put it into the conical flask here, and then we do a titrations. Okay, so what is in here? What do we expect here? Of course, we expect some zinc still there. Okay, zinc chloride, some product because they start reacted for 2 minutes, and then of course we expect hydrogen gas. Hydrogen gas shouldn't be here because it will release off here, so shouldn't be hydrogen gas. And of course we still have the remaining of HCl because the reaction just started for 2 minutes. We still have some HCl in it. So then the titration is actually meant for the HCl. So we use it to titrate with NaOH with known concentration. Let's say this is actually 2 mole per dm cube again. All right, and of course volume, it depends. So we put in an indicator as well to observe color change. So let's say I put in meta orange, so we can identify the endpoints. So after 2 minutes, we quench it. We do a titration with NaOH so that we can find out, we can calculate the remaining mole of HCl. You got that? Just now, before the reaction started, we know the initial moles. Let's say the initial mole is 25 times 2 over 1000, right? Okay, 25 times 2 over 1000. So we get 0.05. So initial mole here is 0.05. So from this titration, we can do a calculation, and then we found the mole. Let's say the mole now is actually 0.03 from this titration. So this will be the number of mole of HCl remaining. All right. Now we can see the drop here in terms of concentration. 0.05 dropped to 0.03. So there is a decrease by 0.02 after 2 minutes. And then we repeat the experiment, which means we take out the conical flask from the ice bath and heat it up. So allow the reaction to progress, allow the reaction to continue. So to continue for how long? 2 minutes again. So we fix the time interval. They will continue for 2 minutes, and then we repeat the process of quenching it, put it into the ice bath again, take it out and do a titration, and then calculate. Maybe now the second round of quenching and the titrations, we got the remaining mole of 0.02 moles. So again, it drops by 0.01. So from 0.05, it drops to 0.03, 0.03, it drops to 0.02 for every 2 minutes. And then we continue here, see how many times we would like to measure. Usually 3 to 5 points is enough to plot a graph, right? So after we got 3 points, let's say for example, okay, we got 3 points, then we can plot a graph. So once we get 3 points, we can plot a graph of concentration of HCl against time. See that? And then the curve will be something like that. Okay, 3 points here, let's say for example, we plot it out, and then from here we can actually determine the rate of reactions. Now this is using the graphical method. And of course you may ask, we have the decrease in concentrations, we have the time taken. Why not we just calculate this straight away? Yes, of course, you can do this. So just now was 0.05 minus the last measurement, let's say 0.01, divided by the time taken, let's say 2 minutes, 2 minutes. Overall, they use about 4 minutes, let's say, overall. And then we can get the 0.04 over 4. Okay, we can get the rate. So the rate of reaction is 0.01. And what's the unit for this? The unit for rate of reaction in this case depends on what we are measuring. We are measuring the concentration, of course, is mole per dm cube. Okay, per minutes. If we are measuring in minutes. And usually the unit for measuring rate of reaction is mole per dm cube per second. Since I'm using minutes here, it depends. All right, but the usual one, the commonly used units will be per second. So you can change that, and then you can get the concentrations or the rate of reactions. You got that? So this is by just calculation. But if we plot the graph out like that, so we can actually measure the rate, the average rate of reactions, the average rate of reactions, which is the overall initial how much, and then at the end final, and then over the total time taken. Or we can actually measure the instantaneous rate. Now, what is that instantaneous rate? Look at this graph that I prepared here. So let's say this is actually concentration of the HCl. We plot it out, and this is the time taken. And the red color is the curve. 1 point, 2 points, 3 points. Now we can measure it. We can measure the instantaneous rate. Let's say, what is the rate of reaction at time equals to 3 minutes, which is here. So we're going up to this point, and then based on this point, we draw a tangent line. See the blue line, tangent? And then we can plot it a triangle based on the tangent line, and of course the triangle must include the 3 minutes, and here we can calculate the difference and then y over x. So divide the x, we get the rate of reactions at 3 minutes. So the difference between using the calculation just now, just use the difference in concentration between initial and final over time, and plot the graph out and get the instantaneous rate. All right, so the graphical methods will give you a bigger picture on the average rate as well as the instantaneous rate. You want to know the rate of reaction at the beginning of the reaction is actually really fast because it's steep, right? And then the rate is actually slow now because it becomes less steeper. And then at the end, it kind of achieve plateau at the end when the reaction stop. Okay, so this is a graphical method that we can use to measure the rate of reaction, and of course it's based on what we are measuring. All right, so let me do a conclusion here before I move on to the next. To measure the rate of reactions, we can measure the mass change if solid involved, and of course we have to take the conical flask to measure initial. You put in 2 grams, right? After 2 minutes, we take it out and measure what is the drop in the mass. Next, we can measure the volume of gas by using the inverted measuring cylinder or gas range, and then we can measure the volume collected over time taken. That's the second method. And the third method we can use is measure the concentration of a reactants, where we can carry out a titration. And of course, titration not limited to acid-base. Acid-base is the common one. It can be a redox reactions, right? We can use an oxidizing agent for a certain reaction. It depends on the reactions. Or we can use a complexometric titration. Still remember we learned in SEM 2. Complexometric is when it involves complex ions. We can put it in indicators and combine with it, and we can observe a color change. All right, that also titrations. So there are 3 different methods here. Number 1, measure the mass change. Number 2, measure the volume of gas. Number 3, measure the concentration change, regardless of reactants or product. All right, as long as you conduct a titrations to determine the concentration of a reactants or a product over time, so we can determine the rate of reactions. All right, so these will be to measure the rate of a reactions. All right, next we look at rate law. Now, what is that rate law? Let's say I have a reactions here. All right, so A plus B change to C. Okay, now, just now we learned to measure the rate of reactions, we can measure the change in the reactants or the change in the product. Now, according to rate law, they prefer to look at the reactants. Okay, they prefer to look at the reactants. So let's say in these reactions, what are the reactants involved? We have reactants A and reactants B, right? And then to form the product C. So what is a rate law? A rate law is something like that. It's a rate equations where we put rate equals to K and write out all the reactants involved. So we have concentration of A, we have concentration of B, power A, power B. See that? And what is your K? K is actually so-called rate constant. We will need to learn how to calculate the unit for this and the value for it. And then what is A and B? A and B is actually known as the order of reactions. Now, what is that order of reactions? Order of reactions will indicate how fast or a reactions happen based on the concentration. For example, if I increase the concentration of A, what happened to the rate of reactions? Compared to if I increase the concentration of B, what happened to the rate of reactions? Now, last time we learned that when we increase the concentration of reactants, the rate of reaction will increase, for sure, right? But then, when we increase the concentration of a particular concentration, let's say I increase the concentration of A with certain order of reaction, that will be different from the one when you increase the concentration of B. And order of reaction can be divided into zero order, it can be first order, it can be second order. Okay, so let's do this. All right, let's do the order reactions now. Okay, let's start with zero order. Zero order meaning that when you have A plus B change to C, and then the rate equations will be equivalent to K concentration of A, concentration of B. And zero order meaning that I have a zero here. When you have zero order means it's power zero. When it's power zero meaning that A is becoming 1. So it's just KB. Alright? Because something power zero is equals to 1. So what does that mean is when you have concentration A to the power of 0, it indicates that A is actually zero order, and the change in concentration of A has no effect on the rate of reactions. That's zero order. Okay, so what about first order? Let's say your B is first order, so you have power 1. That's first order. All right, so what does that mean by first order? First order means when you change the concentration of B double, the rate will be double. So it's directly proportional to the change in the concentration of B when it's first order. So if I change the concentration of B increase by 3 times, the rate will increase by 3 times. If I increase it by 4 times for the concentration of B, the rate will increase by 4 times. So that is first order. You got that? And what about second order? Let me show you an example. If it is second order of reactions, then let's say I have again A plus B equals to C, and then I have the rate equations giving you K concentration of A power 2, concentration of B power 1. Alright, what we can see from here is A is actually second order, B is actually first order. Okay, now how does a second order concentration affects the rate of reactions? So if I increase the concentration of A 2 times, what happened to the rate? The rate will be 2 to the power 2. Okay, again, if I increase the concentration of A 3 times, then the rate will be 3 to the power 2. Alright, now if I increase the concentration of A 4 times, then the rate will be 4 to the power 2. So the increase or the increment of the concentration, you put it as power 2. That will equivalent to the rate of reactions. You get it? So that's how we determine the order of reactions. Now come back to these reactions. Let's say I have an equation like that, and then this is the rate equations. Now you tell me, as an engineer or as a scientist in a factory, and your boss is actually asking you, okay, which concentration, A or B, we're supposed to increase it? And of course, if increase both, then the overall reactions will be, the rate of reaction will be even higher, right? But then in terms of cost, if we want to save costs, if we want to minimize the cost but to achieve certain rate of reactions, which one shall we increase, A or B? Then you as an engineer, you should able to calculate, you should able to tell that A is second order, B is just first order. Therefore, if you increase the concentration of A double, the rate will give you 4 times higher. As compared to B, if you increase it double, the rate will only give you double. So of course, in considering costs, we should increase A rather than B then, right? Because A is second order. So this order reaction is useful to determine whether which concentration shall we increase in a reaction. Of course, this is a simple reactions which involve only A and B. In the industrial process, you have a long chain reactions which involve more than 10 reactants in the whole reactions. So by the time you have 10 reactants, don't tell me you're going to increase all the concentration, all the 10 reactants. That will be increasing the cost, right? So if you have more than that, you have a lot of reactants, then we have to systematically divide them, categorize them, which one is giving you a higher order, and that will actually giving you a higher rate of reactions. So we increase only certain concentration reactants. Certain reactant concentrations. You get what I mean? So that's the purpose of learning why you have different order reactions. Okay, so let me do this again, give you a quick summary here. First order, second order, and then we have zero order, right? So we have 3. So first order is when the concentration of A is first order, then if I times 2, the rate will be times 2, right? If concentration of A times 3 first order, the rate will be times 3. If concentration of A times 4, if you increase it 4 times, the rate will be times 4. All right, same for second order. It depends. It's actually exponentially increased. So let's say A is second order. If I times 2, then the rate will be equivalent to 2 power 2, 4 times, right? If concentration of A second order times 4, then the rate of reaction is equals to 4 to the power 2. And what about zero order? If A equals to zero order, which is actually equals to 1, then if I times 2, what happened to the rate? The rate will equals to not 0, but the same. In other words, unchanged, no changes, right? So if your concentration of A is zero order, but I times it with 4 times, again, the rate will not be changed. It's the same. So let's say the initial rate is 1 mole per dm cube per second. That's the concentration. If I keep changing the concentration of A, but then A is actually zero order, what do you expect? The rate will still maintain as 1 mole per dm cube per second. All right, so that's first, second, and zero order. Now, bear in mind there is a asterisk here. Rate equations cannot be deduced theoretically from the stoichiometric equations, and it may not include all the reactants written in the chemical equations. Do you know what it means? So it's something like that. Let's see. I have a reactions A plus B plus C equals to D, okay? 2C, 2B. Now, by just looking at these stoichiometric equations, can I say that I have only one A here? So this is first order. And I have 2B. Oh, yes. So this is second order. And 2C, this is also second order. Can I do that? No, guys. You're not supposed to just refer to the stoichiometric equations and look at the coefficients. Or I have 2B, 2C, and 1A. So this is first order and second order. What if you have 3C, 4C, 5Cs? Does that mean I have fifth order? No. So we can't actually deduce the order of reactions from the equation itself. All right, from the balance equations. And another thing is they said not include all the reactant. What does it mean? So let's say this equation, you have A, B, C, you got D, right? So the rate equation is supposed to be K, A, B, C by rights, right? You include all the reactants and then you have order of reactions. Depends on what is the power. What if the power for A is zero order, for B is second order, for C is first order. Then what will be your rate equation? K, since A is zero order, then is equals to 1. So we don't have to write it in. So we just B power 2 and then C power 1. Let's say, for example, if that's the case, you see that from the rate equation itself, we don't see any A involved. But then from the equation, A is actually one of the reactants. Okay, so this is what they're trying to say, that it may not include all the reactants. It depends on the order of reactions. Because some reactant, yes, it is part of the reactions, but this reactant can be zero order. If it is zero order, it shouldn't be in your rate equations. So everything comes back to this order of reactions before we determine the overall rate equations. All right, and how can we deduce the order of reactions? There are two ways of doing that. Number one, we can base on calculations, which I'm going to show you in another video. And next one is based on the graphical methods. The patterns of the graph can tell us whether this is first, second, or third, or first, second, or zero order. All right, let's look at this. Okay, now order reactions, like I said, is actually the concentration terms A to the power of 2, which is second order. If you have a concentration terms A to the power of 1, which is first order, if you have concentration A to the power of 0, which is equals to 1, then it means it is zero order. Okay, so this is order reaction. We look at the concentration terms of the rate equation and see what's the power. So the basic definition is the power to which a concentration term is raised to. That is order of reactions. All right. Now, zero order, I've explained that, but look at the graph. If you have zero order, you will have a graph like that, rate against concentration, and you have a straight line here. So that makes sense, because when I said zero order means that the concentration change, yes, the concentration is increasing across x-axis, but then you see the rate remain the same as x at this value because the line is horizontal. So no matter how you change the concentration of a zero order, the rate remain unchanged. So when you see a graph of rate against concentration and you see a horizontal line, that means it is zero order. All right, so the next one, look at this graph. It looks different, right? Because the axis is different. I'm using concentration against time. All right, so please be aware of this. Different axes giving you different patterns. So for zero order, when you have concentration against time, the line will be a negative gradient straight line. See that? It is a straight line. Straight line indicates what? Now, when you have a graph of concentration against time, when you divide them, y divided by x is actually equals to the gradient. And the gradient is actually equals to concentrations over time, right? In this case, y is concentration, x is time. So it's equals to gradient, gradient is equals to concentration over time, which is equivalent to the rate of reactions. Okay, so the gradient is actually the rate of reactions. And look at that. You have a straight line, linear curve like that, all the way down. What does it mean? It tells you that the gradient remain unchanged, right? And that makes sense if it is a zero order. So when concentration over time, the concentration of that particular reactant, which is zero order, would decrease over time. It would decrease over time because it's a reactant. But the rate remain unchanged when the concentration of this particular reactant changing, decreasing. You see that? Because it is zero order. All right, so please remember these two patterns of graph for zero order. Next one for first order, we have the first graph, rate against concentration. Again, look at that. If it is first order, like I said, is directly proportional to the change in concentration. If the concentration times 2, let's say from 1 to 2, all right, the rate should be changing from 1 to 2 as well. Okay, and then keep going. So therefore, it's a straight line, a linear line passing through the origin. That's for first order. All right, what if I change the axis into concentration against time? Again, concentration against time, the gradient of this curve is equals to the rate of reaction. Look at how the rate change. the gradient is a curve. All right, this is a curve. So meaning that the gradient is changing over time. Okay, or the rate is changing over time, but it's proportionally changes against time as well as the concentration. So it's a curve like that. Okay, the gradient is changing. Make sense? So these two graphs, the pattern is for first order reactions, and then we have second order. First graph again, look at that, rate against concentration of A, for example, any reactants. So it exponentially change when the concentration increase from 1 to 2, double. All right, from 1 to 2, the rate isn't equals to 2, equals to 4, and keep on going. That's why you get an exponential curve. All right, so this is second order. And what if I change the exist into concentration against time? It seems like the curve, it looks like the same as the one in the first order. Now, first thing, why is it the same pattern? Because when concentration decrease over time, the rate will change over time as well, right? Because the second order is changing, not zero order. All right, the second order meaning that you have some effect on the rate of reaction. So the gradient is changing, meaning that the rate is changing over time. That makes sense. But then why are they looking the same? Huh? Why are they looking the same? Look at that. You have a concentration against time for first order, and then for second order, it looks the same. And how do we actually differentiate them? Which curve is second order? Which curve is first order? Then we have to look at this thing called half-life. Now, what is that half-life? So let me show you the detail. Half-life is something like that. Let's say I have a curve like that, right? Okay, I have another curve which is also like that, and this is concentration of A against time. This is concentration of B against time. All right, they both look the same. So can you tell whether it's first order or second order or zero order? The answer is it is definitely not zero order, because zero order is supposed to be a straight line, negative gradient, okay, linear. So they show a curve, so it's either first or second. Makes sense? But then how do we know which one is first, which one is second? It can be both first, it can be both seconds, right? So we use half-life. How do we calculate half-life? Half-life meaning that when the concentrations of a reactant drop by half, what is the time taken? That will be the half-life. Let's check. When the concentration of B started with 0.5 initially, it drops to 0.25, right? So what happened when 0.5 dropped to 0.25? That's half from here to here, right? And what's the time taken? Then you plot the graph, extrapolate, and all the way to the time. So X is given. Let's say the time taken is 2 minutes. All right, and then these 0.25 decrease half again. All right, 0.125, and what's happened to the time? The time taken is here, 4. Let's say, for example, and can you see that first half-life from 0.5 to 0.25 is actually 2 minutes. Second half-life from 0.25 to 0.125, the difference is also 2. So I can say this is actually with a constant half-life. When you have a constant half-life, it means it is first order. All right, let's look at another graph. Let's say I am starting with 0.5 again, and then it decreased to 0.25. So what's the time taken here? Let's say 2 again, right? From 0.25, it drops again. So 0.125, half again. All right, here is actually 6. So look at that, 0 to 2. So different is 2 here. From 2 to 6, different is 4 here. So the half-life is actually increased from 2 to 4. So what happened when you have increasing half-life? When you have an increasing half-life, that would means this is a second order reactions. A is second order from the graph. B is first order because constant half-life. So then we can write the rate equation. Rate equals to K, concentration of A is 2 and concentration of B 1. So that's how we deduce the rate equations and the order reactions based on the graph. Make sense? So we use half-life for this. All right. So let's look at these reactions again. For example, I mean something chemical instead of A, B, C, D, right? So we have propanons here plus iodine. You get these products, okay? And this reaction is catalyzed by an acid, okay? So what are the concentrations of reactants involved? We have this, and then we have a catalyst. Now look at the rate law. Rate equals to K. Concentration is propanon. Yes, we have that. Concentration of H plus. Wow, look at that. Catalyst is actually part of the rate equations. Catalyst is not a reactant, but why is it in the rate equations? And then do you realize that iodine is not there? What about iodine? Iodine is not there, but is part of the reactants. It means concentration of iodine has no effect on the rate of reactions, meaning that concentration of iodine is 0 order, right? So from there we can deduce. And what happened to the concentration of this? Look at that. It's nothing there, means first order, and this one H is first order. So even a catalyst can be a first order. And why? Because catalyst does affect the rate of reactions. Catalyst can increase the rate of reactions. When you increase the concentration of the catalyst, although the effect is not that obvious, but still, when you increase the concentration of the catalyst, we expect the rate to increase further. Right? So in this case, from the rate equation, it can tell you that, okay, certain reactant has no effect, so no point actually changing the concentration, like iodine in this case, but then the propanon and also the acid catalyst, the acid, the H plus in this reaction are important in terms of rate of reaction. So we should actually consider to increase the concentration of the acid, which is the catalyst, or the concentration of the propanons from the rate equations given. All right, so this is how we deduce when you have a rate equations. All right, now this is just a summary on the first, second, third, first, second, I always talk about third. It's first, second, 0, all right, for different graph. The first row here is actually for rate against concentration. The second row at the bottom is actually concentration against time. And then I actually highlight the pattern of the graph. So this is 0 order, straight line. Proportional passing through origin, first order, and then exponential curve, second order. But when you change the axis to concentration against time, we focus on the gradient. 0 order, gradient remain unchanged. First order, gradient change. Second order, gradient change. Look at that. This is much clearer. First and second order, you can see they're both curved, but then second order giving you a steeper curve. All right, but then the most accurate way to determine whether it's first or second based on the graph is to calculate the half-life, is to determine whether it has a constant half-life or increasing half-life over time. Then we can tell whether it's first or second order. All right. Okay, I guess that's it for the first video. These will be the introductions for how to measure rate of reactions, what is rate law or the rate equations, how do we write that based on the equations, and what is order reactions and how do we differentiate between 0, first, and second, and as well as the patterns of the graph for 0, first, and second order. All right, so I'll see you again in the next video where I'm going to show you how to calculate or how to determine order reactions based on calculations. All right, thank you guys.